Hey y'all, welcome to class today. We'll give you guys a minute to hop in. I hope you guys are staying nice and warm and dry because it's raining again today. How is everyone today? Are you guys doing okay? Good, I can see you guys are popping in. Feel free to say hey in the chat box so everybody knows you're here. I'm good, things are great. It's just great. Everything is great. Glad you guys are all here and hanging out. If you have any questions about anything from the course, feel free to drop that in the box. I'll answer that in here in just a second. We have Alex due this week. Don't forget your mini exam 2 is next Monday, so in several days. Ooh, Christopher asks, how much does the mini exam go over on Monday? It goes through the end of this week's material. So it's all of chapter 4 and the beginning of chapter 5. So the questions from last week or this week will be on the mini exam. That is on Monday. Good question. Other questions? Any other questions, comments, thoughts before we get working on the problems today? If you've looked at the worksheet for today, questions 5 and 8 are pressure volume work, which is, we will solve those problems today, but they're actually in the videos for next week. I didn't realize that after I posted it, and I just left them up there because it was easier. I will give you the answers to those today. We'll go ahead and work them on the board, but they are not on the mini exam. They're part of the next group of videos. So the mini exam goes through last week and this week's material. So the new stuff for next week will not be on the mini exam. It will run just like mini exam 1 on Canvas. Same deal, make sure you upload your work and all the rest. It is not on Respondus. So it is more of an honor code situation where you make sure you're working by yourself. Any other questions before we talk about today's material? Make sure I didn't miss any in the box. I don't think so. Haynes, it's questions 5 and 8. Oh, way to go, Sterling. Other questions? The Alex this week has some tricky questions. I'm going to solve ones that are quite similar. So when we get to those, I will point out which ones, hey, this is definitely part of your Alex homework. Make sure that you are thinking about the questions in this way. Because I know that sometimes Alex asks you really tricky questions to kind of really ask, like, do you know what's happening? And I want you guys to know what's happening. Okay, so our first question, oh my gosh, Hope. Alex tries you. It does try your patience, but I promise that it is so much better in the grand scheme of things. Miri says that there are extra worksheets at the SAS tutoring, which is totally true. There are also additional worksheets if you hit up SI. So I know that those are this week, I think. Test your patience. I know that Alex can be quite frustrating. Don't forget that on Mondays, including this upcoming Monday, although I'd recommend that you finish your homework before the mini exam, from 4:30 to 6:30, I'm in a Zoom room, and if you get stuck on an objective, I'm happy to help you. So if you have issues, please let me know and we'll just kind of figure that out. So our first question is how many grams of calcium hydroxide are needed to neutralize 97.21 mils of the 1.25 molar nitric acid? So this is a neutralization. It's a part of a titration. So today we're mostly going to focus on titrations. Make sure that you have reviewed the oxidation numbers video. I don't have any examples on that, but there are lots of questions. I'll make sure it's in your ALEX objectives if it's not already. Those will be on the mini exam. So make sure you look over those. We will not overly focus on the activity series, just heads up. You will probably need that information for lab, but we will not be testing on the activity series. So in this question, the very first thing we need to do is write a balanced equation. So we know that we have calcium hydroxide, so calcium CaOH2, we're adding it as a solid. So we're going to basically drop solid calcium hydroxide into an aqueous solution of nitric acid. So when we do that, the question becomes, what is the balanced chemical equation? So the bigger issue is that a lot of times students forget that we need to balance our equations. So more than likely for a titration, you will be given an acid and a base, and you need to balance them. So in this case, we're going to get calcium nitrate, aqueous, plus H2O, liquid. So in this case, the calcium nitrate has 2 nitrates, so we need to put a 2 here. And by doing this, we have the 2 hydroxides and 2 H pluses. So we're going to put a 2 here. So I'll bring you all a little closer so it's a little bit bigger. Not just myself. Okay. Sorry. Now the question asks, we have a balanced chemical equation. So we need to know how many grams of calcium hydroxide are needed to neutralize that quantity of nitric acid. So in this case, we're using the information from chapter 3 where we can determine reactant to reactant or product to product by using the balanced chemical equation, which we now have. So we're going to use the molarity and the volume to determine the moles of nitric acid. So we're going to take our 1.25 moles in 1 liter, and we're going to multiply that by the volume, which is 0.09721 liters. So this is our volume, this is our molarity, and that's going to give us 0.12054 moles of HNO3. So once we're able to use the molarity and the volume to calculate the moles, now this looks very similar to a moles to grams calculation using a balanced chemical equation. So we're going to take our 0.12054 moles of HNO3, and we are going to convert that to grams of calcium hydroxide. So there are 2 moles of HNO3 for every 1 mole of calcium hydroxide, and 1 mole of calcium hydroxide weighs 74.01 grams, and we got 466 grams. And based on our question, we only can have 3 significant figures. So our final answer would be 4.47 grams. So what questions do we have about molarity, which we talked a lot about last week, or titrations? Or what questions do you have about this question in general? If you have no questions or you thought it was easy, feel free to write that right in the chat box so that I know. Nice, Mary. Good. I'm glad you guys are getting it. We'll give it another couple seconds, see if anyone has any questions before we move on to number, ooh, we have a question. Yeah, Hope. So Hope asks, can you explain how you went from big M, molar, to moles? Sure. So, give ourselves a little bit more space. So big M, is equal to moles divided by liters. So if you have 2.5 molar, that equals 2.5 moles in 1 liter. So by taking the 1.25 molar, I find that I like the ability to cancel units. So the ability to cancel units means that I need to take the molar apart. So I take it apart and basically say it's that number of moles in 1 liter. So if you calculate the molarity, you determine the number of moles and divide that by the liters. So I just took that unit apart to help me cancel things out so that I could use molarity kind of like density. We used to use density or a different conversion factor. Does that answer your question, Hope? I think I'm going to double check the comments, make sure I didn't miss any other questions. Sweet. So now, you guys can start plugging away at how many milliliters of 2.34 hydrochloric acid are necessary to neutralize 145 milliliters of 1.49 molar strontium hydroxide. So the first thing is a balanced chemical equation. So our first thing is that balanced chemical equation. So we have hydrochloric acid, H, right? Yep. HCl, aqueous, plus strontium hydroxide, also aqueous. And that's going to create strontium chloride, which in terms is aqueous, plus H2O, liquid. Now from here we need to make sure we have a balanced chemical equation. So there are 2 chlorides on the left, so we'll add a 2 here and a 2 here. So now we have a balanced chemical equation. This question is very similar to the last question, except it's asking for a different component. This one is not exactly like, but very similar to the material you'll see on Alex. So in this case, it's asking us how many milliliters of the 2.34 molar do we need in order to neutralize? So what we need to do is figure out the equivalent moles of hydrochloric acid and strontium hydroxide, and then we can go from there. So the first thing we're going to do is use our molarity and our volume to determine the moles of strontium hydroxide. So we're going to take our 1.49 moles in 1 liter and multiply that by 0.145 liters, and that gives you 0.21605 moles of strontium hydroxide. Now, from here, we need to convert that to moles of hydrochloric acid. We're going to do that using the balanced chemical equation. We're going to take our 0.21605 moles of strontium hydroxide. Using the balanced equation, there's 1 mole of strontium hydroxide for every 2 moles of HCl, and that gives us 0.4321 moles of HCl. Once we determine the moles of hydrochloric acid, sometimes it asks for the concentration, but in this case we know the concentration, so we're being asked for the volume. So now I'm going to use the molarity of the other solution. So the hydrochloric acid is 2.34 moles in 1 liter. Do I have enough space over here? Yeah. And so that's going to give me 0.18465 liters. And our 0.18465 liters. In 1 liter, there's 1,000 milliliters, which is 184.65 liters. Nope, milliliters. And based on the problem, we can only have 3 significant figures, so that transforms into 185 milliliters. Now, a common question is, do I have to show the work just like this? So it turns out no. Ordinarily, if I was going to set this up, I probably would have done one long set of equations and just gotten a final answer. But I like to break it up this way so that later when you review your notes or rewatch the video, you can remember what the role of each step was. So the first step is to determine the moles of strontium hydroxide. This is the same as a grams to moles calculation. From here, we're going to use a balanced chemical equation to determine the moles of hydrochloric acid. From here, it asks what volume of the 2.34 molar solution will give us this amount of moles. So we can use the molarity to determine that. Then using our significant figures and converting to milliliters, we got 185 mils. So what questions did you have about this calculation? If you thought it was easy, you can drop that in the chat. If you have other questions. Basically, what questions do you have? And if you don't have any, feel free to drop that in the chat, and that'll be great. Nice, Jenna. I'll give you guys a little bit longer in case you have a question percolating around. Great, Hope. I'm glad you're following along and getting it now. Nice, Matthew. Muri asks, how many questions does the mini exam have? You should expect it to be similar to the first mini exam. So roughly a quarter that there were on the exam. Somewhere, it's the exact same 22 minutes, somewhere on the order of probably 8 to 10 questions, but I don't really know yet. But a great question. So, this question. If you have not started your ALEX for this week, this question has the potential to be very irritating. Or, as many of you said, it really irks you or it tries your patience. This one will try your patience. So, I'm going to tell you how to do it. Hope asks, what's the time frame we can start it? It will be between 4:30 and 5:10. That way you can finish before you can be completely done prior to the review session that I'll probably run in Zoom like I did at the end of the first one where I go over the exam. So, the first part of this question, kind of like everything else we've done today, is let's write a balanced chemical equation. So in this case, we have 1.47 grams of iron 2 iodide, and it's going to be dissolved in 200 mils of a 24 millimolar solution of silver nitrate. And it asks us, what is the concentration of the iron ion in solution? So, let's write our balanced equation. So we're going to start with FeI2 plus silver nitrate, and we know that that's aqueous, so this adds in as a solid. And so from here, we can go to FeNO3, 2, aqueous, or we don't know that yet, plus AgI. So we're going to balance that by adding a 2 here and a 2 here. So, balanced chemical equation, step 1. Step 1B is to ask ourselves what is soluble and insoluble. Now, the problem is we just assume that everything is soluble or insoluble and kind of don't think about it. So we want to, our plan, I'm sure you'll all be seeing, 1, balance equation. 2, check solubility. So in this case, if we look at our table, this is soluble, which is good because that means it will dissolve into the liquid. We already know that the silver nitrate is soluble because it's in the solution. Iron 2 nitrate is going to be aqueous because there are no known insoluble nitrate compounds. Nitrate is always soluble. AQ. And then it turns out that the silver iodide is solid. So, now we have a balanced chemical equation with our solubility. So the question becomes, what is this question asking us? Suppose we have a mass dissolved into a liquid, and it's asking us about the concentration of the ion. Now, the iron here, it turns out is in an aqueous compound here. So the concentration of iron in this compound is going to be the same here because it is soluble. So part 3 has 2 parts. We're going to ask, where is the ion? And 2, limiting reactants. So, we also know how much silver nitrate we have. We can now start to ask, what is the limiting reactant? Now, sometimes we need that information and sometimes we don't. In the case of the iron nitrate, as soon as the iron dissolves, it is in the final solution. So it's not an excess reagent or a limiting reactant. So in this case, we're going to take our 1.47 grams of FeI2 and convert that to moles using the 309.65 grams in 1 mole. And that gives us 0.004743 moles of FeI2. Now, the next part of this, account for the ratio in our compound. So there, for every 1 mole of FeI2, there's 1 mole of Fe plus. Now, in this case, it seems kind of silly to think about this, but if they had asked about the nitrate ion, we would have to take into account if there's 1 nitrate or 2 nitrates. So from here, we're going to take our 0.004747 moles, divide this by our total volume, which is 0.200 liters, and this gives us a 0.0237 molar of the Fe plus. So, I know this was a lot, and if you haven't looked at Alex, it feels like I'm telling you a lot of things that seem quite irrelevant. Oh, sure thing, Possum King. I will make bigger decimals. Always happy to help. If there are other things that you can't see the way I've written today, I'm trying to write bigger, but I can see in the video that the balanced equation gets a little smudgy. Sorry about that. What questions do we have about this part? In a second, I'm going to talk about what do we do if it's not. So we're going to look at what if it was asking about the iodine ion. But in order to do that, I'm going to erase everything on the board. So I will obviously move out over to the side. So you can look at that for just a second. Then we're going to ask ourselves, what is the concentration of iodide ions at the end? So I'm going to put here a star and say, what is the iodine ion concentration? Oh. So what we're going to do next is we're going to ask ourselves a different question. What if, instead of asking about the iron concentration, it had asked about the iodine concentration? Now, it would be the same process. We balanced our equations, we checked the solubility, but the iodine goes into solution, or goes into the solid. So it is possible that there is 0 left if it's limiting reactant, or there could be some excess. This is one of those Alex ones where if you get 2 right in a row, it's going to try to trick you the next time and really try your patience. So we're going to start by doing this the same way. We're going to take our 1.47 grams of iron iodide, convert to moles. Except here, we are going to convert to, we have this moles of I2. How many moles of iodine only? So for every 1 mole of FeI2, we have 2 moles of iodine. And I'm going to use my phone to answer this because I forgot my calculator again. So in this case, we have 0.00949. 6 moles of iodine. So the other thing we need to know is how many moles of silver we have. So we can now use the concentration and the volume to determine the moles of silver. So we're going to take our paper. We're going to take our 200 milliliters. So we have 0.200 liters. We're going to multiply that by the 24 millimolars. Millimoles in 1 liter. There are 1,000 millimoles in 1 mole. So now we have, our 0.2 multiplied by 24 divided by 1,000. So there are 0.0048 moles of silver. We'll say silver nitrate. For every 1 mole of silver nitrate, there is 1 mole of silver, which tells us that there is 0.0048 moles of silver. Oh, I forgot to keep my decimal points got small again. Hold up. So, now, this feels like we're going off into like the deep end. I love it. So now we have determined how much iodine and how much silver there is. We know that they need to be in a 1-to-1 ratio. So we need to figure out what is the limiting reactant, because the limiting reactant will tell you how much is left. So in this case, we're going to take our 0.0048 moles of silver, and for every 1 mole of Ag, we get 1 mole of AgI. For every 1 mole of AgI, we have 1 mole of iodine, which means we need 0.048 moles of iodine. Now, if we look back, we have 0.009496, so we have more iodine. So if the question asks about the iodine ion, there is going to be excess. So the iodine ion concentration would be 0.009496 minus 0.0048 mole, which gives us 0.009496 minus 0.0048, which gives us 0.00469646. I'll have to move you up, and I need a little bit more space. So, do it this way. So now we have our 0.004, we'll just keep moving, 46946 moles of iodine. The question asks, what is the iodine ion concentration? So now we need to divide that by the volume, which in this case is 0.2 liters, which gives us 0.023473. Molar, or sig figs, are 0.0235. And I don't think y'all can see that, so let me move this thing to where you guys can get a better view. Questions? Hi, Jane. I like your question. It says, hold up, are we just looking for other components' concentrations? In the case of this question, yes. So when you see this objective on Alex, it will give you two things and then ask for one of the 4 ions. It turns out the one that I picked is misleadingly easy. So it is possible that you will be asked to do something this complicated for this question. Sterling asks what is definitely not a dumb question. Why do you have to do all of this for iodine but not for the iron? So the iron, this is the best question you could have asked. So the iron iodide is soluble, so it dissolves into its ions in solution as soon as you add it for this. The iron nitrate is a soluble product and not involved in the precipitate. So in that case, the iron, whatever goes into solution stays in solution. For the iodine ion, the reason we have to do all of this, because I will admit this is a lot. It feels way overkill. But for the iodine, the reason we have to do all of this is because it's part of the soluble, or because it is part of the solid. So the question is asking what's left over if it's part of the precipitate, or if it's not part of the precipitate. So the way you'll see this gives you, there are basically one of 3 answers. 1, is it soluble on both sides? The the molar concentration is just the moles divided by the volume. Is it on both sides, and is it the limiting reactant? If it's the limiting reactant, the concentration is 0. Or it is this, where it's part of the precipitate, but is the excess reagent. And so you have to calculate how much is removed out of solution and what is left over. So Ashana asks, how do you know if something is an excess or if it is a limiting reagent? The same way you would look at it back in chapter 3, where we convert reactant to reactant and then look to see. So that's this calculation to figure out how much silver we had per mole. So then we could figure out whether or not this was the limiting reactant or the iodine was. You could also do this on the molar components. It will also work. It'll just take you a little bit longer. So Christopher asks, how did you get 0.009? Which feels a little bit like I did math wrong when you ask it that way. So I got the moles of iodine. Sure, Sergey. Let me give you a pretty flat. Sorry, I know you asked me to get out of the way. I'm moving. If you would like to take a screenshot or a picture of the video, I will not get back in the video, so you can take that picture. But to answer Christopher's question, so he had asked, where did that number come from? I needed to determine the quantity of iodine that is independent from the moles of iron to iodine. And so the way we did that was by converting the moles of iodine, the moles of iron to iodine, to just the moles of iodine. So I multiplied the moles of that by 2 because the moles of FeI2, 1 mole of that contains 2 moles of iodine. Not a problem, Sergey. Happy to move out of the way. If you'd ever also like to do that, I'm more than happy to just move out of the way. So Hope asks, if the silver was greater than the iodine, and it would be limiting, and the answer is 0. That is correct. So if, and that doesn't really make sense in here. Oh man, I forgot to keep my decimals large. Sorry guys. If this value had been 0.01, hypothetically, that is more than this. So this becomes the limiting reactant. Therefore, there is none left to go in solution. Totally correct. What other questions do you guys have about this calculation? This is probably, I don't know if it's the hardest one today, but it is one of the hardest objectives you'll see this week on Alex. Other questions? Anyone else need to take a screenshot? I'll step out of the way. Otherwise, we can move on to question number 4, which I will go ahead. I'm going to step out for a second so you guys can take that picture. And now we're going to go ahead and put up question number 4. So you guys can, whoa, lots of words. So I'm going to leave that up there so you can read it while I erase the board, and then I will read it, and then we'll solve it. Sterling asks, how do you know which one is the limiting? You would compare the moles of both, and the one that has the fewer moles is typically the limiting reactant. It's the same as it would have been in chapter 3, where you compare moles to moles or grams of one to the other to determine the limiting reactant. That's just the same limiting reactant we learned in chapter 3, but now it's including molarity and precipitation. So I really love a good multi-component question. All right, this way, hopefully everyone can see everything. So this also comes very similarly from Alex. So a student needs to standardize a fresh solution of sodium hydroxide. He carefully weighs out 1.28 grams of oxalic acid, which this is the formula for that. It's a diprotic acid, and dissolves it in 225 mils of distilled water. The student then titrates the oxalic acid solution with his sodium hydroxide solution. When the titration equals the equivalence point, the student finds that he has used 17.3 mils of sodium hydroxide. What is the concentration of the sodium hydroxide solution, in this case in molar? So, first things first, balanced chemical equation. So this one feels a little different because this is not one of the standard acids and bases that are in the slides that say memorize. But it tells you how many protons it has. So an acid gives off a proton, and a base gives off a hydroxide, give or take. When it says it's diprotic, that means it has 2 protons. If it's dibasic, it has 2 base units. So now it will basically tell you whether the equation is 2 of one to 1 of the other. But you can balance that equation. Make sure I'm in the right space. H2C2O4 plus 2NaOH gives us 2H2O plus Na2 oxalate, which is C2O4. So if I give you a non-standard acid or base, I will tell you how many protons or base units it has. That basically says that the other one, you need more equivalents of that than the other. On both the mini exam and the exam, there will be no one-to-one titrations, which means if you use M1V1 equals M2V2, you will get it wrong. Just saying. So now it asks us to calculate the molarity of the sodium hydroxide solution. So first, we need to calculate the number of moles of the oxalic acid. So we have 1.28 grams of oxalic acid, which is H2C2O4. Using the molecular weight of 90.04 grams and 1 mole of H2C2O4, that will determine the moles of oxalic acid. We need to then convert that to the moles of sodium hydroxide. So we have 1 mole of H2C2O4 for every 2 moles of NaOH. And that gives us 0.0284 moles of NaOH. Good, that's still in the frame. So now we need to determine the concentration. And concentration is just moles per liter. So we have our 0.02843 moles of sodium hydroxide, and we want to divide that by the volume. Now, in liters, so we're going to take our 17.3 milliliters and convert that to liters, 0.0173 liters, and we get 1.64 molar NaOH. So I think this one also came pretty similarly out of Alex. So I'll check. Oh, sweet. What other questions do you guys have about this question, if you have any? This is easier than the last one. And it's good that you might feel that way if you didn't get lost in the last question. So the other way you might see this is provided with a molarity of the oxalic acid, but your first step is to convert to moles, then moles to moles, and then the calculation or the concentration. So what questions do you guys have about this question? Any questions? Oh, I gotta get out of the way. Sorry. If you thought this was easy, go ahead and write easy in the chat so that I'll know that we're ready for number 5. And I lied. We're going to move directly to number 6. Ooh, Muri asks, we never used the 225 milliliters because it was never asked for. That's correct. So if it had asked what is the concentration of oxalic acid, then you might have needed that information. But in terms of this calculation, it was unnecessary. Dean, it was definitely for show. There are versions of this question where you might have needed that information, but in this case, you do not, the way this is set up. Good questions, you guys. So I'm going to go ahead and put up the next one. So this next one is also one out of Alex that may or may not, I don't think it will be as frustrating as the earlier one, but it can be problematic. So the remainder of today's worksheets are from chapter 5. So I mentioned earlier that you should make sure you work some example problems on oxidation numbers. There are lots of examples in the video, but those will be on the mini exam. We just don't have any examples today. They're also in the chapter worksheets. So from here until the end of today, we're going to talk about chapter 5. Chapter 5 is going to start to talk about energy. And so we're going to start to need to have equations. So there will be an equation sheet on the mini exam. It'll be the last thing at the end. So it's like sign your name, periodic table, all the questions, equation sheet, the thing that tells you the exam is over so that you know you've seen it all, right? It'll be there like it was on the exam. So in this equation, in this question, it says the temperature of a water bath is monitored, and it's determined from the data that 307 kilojoules of heat flowed out of the system during a reaction. The system has a piston, and it shows that the piston does 287 kilojoules of work on the system. What is the change in energy of this reaction? This question is tricky and not all at the same time. So the change in energy in the system is calculated from a really simple equation. Delta E equals Q plus W, where Q is heat and W is work. Now, the biggest issue with this problem, I'll move you guys a little bit closer, is that it's not just Q plus W. You're not just going to add the two numbers, because we have to determine the sign of those values. Is the work positive or negative? In the slides, I've made a really great table for you guys. I would recommend that you make that part of your note packets or your study guide, because I'm going to ask questions, and it matters whether the heat is gained by the system or lost by the system, or gained or lost by the surroundings. So if the system gains heat or the surroundings lose heat, that's the same. So in this case, the heat is lost from the system, so Q equals negative 307, and work is positive 287. So delta E in this case is negative 307 plus 287. These are both kilojoules. And that's going to give you negative 20 decimal place kilojoules. So the hardest part of this calculation is determining if the work is done by the system or on the system. When I solve these problems, I look at that table and I say, which of these is the way that that occurs? Is it this or that? So, what questions do you guys have about this calculation? The next one that we do will be, I don't want to say the same, it's just going to be a different version of this calculation with different numbers and perhaps written in a different way. For those of you who are asking, or maybe like, what is a piston? In Alex, it's going to give you a graphic. So we have a tank. We have a water bath. So there's water in here. And on this side, there's a tube. And it basically has a valve. And so we're going to measure the temperature. And then either, if the system does work, it's going to push this down, so it's going to compact the system. If the surroundings do work. If the system does work on the piston, it's going to push the piston up. So sometimes these questions will ask you different versions of that. Sterling, I'm glad that this one's good for you. Any other questions? We can go ahead and put up number 8. Whoa. So Jenna asks, can you explain, oh, she says, wait, never mind. So, good job. Elizabeth says, so in Alex, it asks you what is the change in energy. I will ask you what is delta E. So the way Alex words that question, they are asking for, Alex is asking for the absolute value of the change in the way that they've worded it. I will ask you what is the change in energy for this reaction, kind of like it says up here. And so in that case, the answer is negative delta 20. No, delta E equals negative 20. Alex is asking for the magnitude of that value. I will ask you for the absolute value, like the actual value. And Jenna, that's not done. It's a great question. So let's move to number 8. So happy to help, Elizabeth. In this question, it asks, what is the change in energy for a system that releases 12.4 kilojoules of heat to the surroundings and does 4.2 joules of work on the surroundings? So you'll notice that the difference between these two questions tells us about the sign differences. Some people talk about the system only, and some people talk about the surroundings, and sometimes it changes. One question could be about this, and the other one could be about something else. So we're again going to calculate delta E, but first we need to determine Q and W. So in this case, Q is negative 12.4 kilojoules, and W is negative 4.2 joules. So in this case, because the heat is released to the surroundings, so the system lost heat, and the work, and it does work on the surroundings, so it's losing work, they're both negative. So our delta E in this case is negative 12.4 plus negative 4.2, and that's going to equal negative 16.6 joules. So again, these are easy if you can assign the signs. And once you figure out the pattern, it's much less complicated than perhaps some of the other ones where you're trying to figure out what part of it is right or wrong. So this is the end of the stuff on the mini exam, because the next two questions, calculating work using P delta V, it turns out I thought that was part of the 5.1 video, but it's part of the 5.2. So I am going to go ahead and solve those so that you have them, but it will not be on the mini exam because it's not part of the videos. So any questions before we solve two of a different type? Doesn't look like it just yet. So we're going to solve number 7 first. I'll let you read that while I erase. So Mary, are you asking about number 8? So Hope asks, if it's in kilojoules, that doesn't affect the equation. No, that's just a magnitude of that. I got a lot of comments happening all at once. So Mary asks, absorb is a positive sign and release is negative. It turns out that it matters how that's defined. So if it is absorbed, it matters if the system absorbs or the surroundings absorb. And so it is important to know that it matters. You can either think about the system or the surroundings, but using the word absorb and release as the way to define those two things may or may not give you the right sign all of the times. It matters if the system releases heat or the surroundings release heat, because one of those is positive and one of those is negative. Oh, Sterling, I think you're correct. I think that I can't do. So what did I say? 5 and 8? Yeah, apparently it's 5 and 7 are not on the mini exam. I am so sorry for the confusion. Five and 7 will not be on the mini exam. They also will not be solved next week, which is why I'm going to do them today. So the calculations are super easy, and we will be able to basically just take this information and file it away for when you need it next week after the mini exam. That's all it is. But in order to do this, in this case, the question asks, a mixture of krypton and hydrogen gas is expanded from a volume of 82 liters to 95 liters. When the pressure is held constant at 36 atmospheres, calculate the work done on the gas mixture in kilojoules. In this case, we are using something out of the next week's videos. So the equation we're going to think about is how do we arrive at work? And so work can be arrived from basically knowing the sign, or we can do something called pressure volume work. And that equation is P delta V, where P is the pressure and delta V is the change in volume. And so in this case, it is again a pretty simple equation where we're just going to plug in our numbers. So the pressure in this case is 36.0 atmospheres. And our delta V is V final minus V initial. And so in that case, the V final is 95.0 minus 82.0. So delta V is 13.0 liters. So now we're just going to plug this into our calculation or into our equation, where we have a pressure of 36.0 atmospheres multiplied by the volume of 13.0 liters. The problem is, and the reason this can be just slightly tricky, is that it asks for it in kilojoules right here. But if we look at this equation, when we multiply those two values together, our answer is in liters times atmospheres. So it turns out that we want to convert that into kilojoules. So there are 101.3 joules in 1 liter times atmosphere. This is a conversion factor. And so a conversion factor is the same as if you wanted to convert miles to inches or anything else. And so when we plug this in, we will get negative 474.08 joules. There are 1,000 joules in 1 kilojoule. And this gives you negative 47.4 kilojoules. Sorry, Jane, I just looked at it and realized that I'd left the negative sign off. The negative sign should be there, so we have negative 36 times 13, which gives us negative 47,408 joules. And once we convert that to kilojoules, we get negative 47.4 kilojoules. Nope, feel free to ask because it's always possible. I just forgot about it. Questions about this calculation? I know we haven't watched the video or anything else. Any other questions today? I think instead of working the other question, I think that's question 5 about the scuba diver, we will just stop here for today. Instead of trying to teach you new information, we will try to fit it in next week in the problem solving session if it fits. Any other questions today? Thank you. I'm glad you're here today, Audie. So other questions today. Otherwise, we can head out and I will see you all next week. If you are rolling out, feel free to say see you later in the chat box. If you guys would like, you can also say go ahead and do the other question. It's kind of up to you. But we will solve the scuba question next week because I feel like we've moved a little further than you guys were ready for today. Other questions? Otherwise, y'all have a great rest of the day and try to stay warm if you're not based in Florida right now. Bye, Possum King. Jane, are you asking about the questions from the heat and work, or are you asking about work equals negative P delta V? Because, oh, I lost your comments. Those of you heading out, y'all have a great rest of the day. I'll see you next week. As always, email me if you have questions, or feel free to come to office hours or SI, which is tomorrow. Sure, Jane. So when we think about heat and work, there's a table in the 5.1 slides that I think you probably want to write down. But when heat is lost from the system, heat is negative. When heat is gained from the system, when the system gains heat, heat is positive. So it matters if the question says, the system gains heat, ooh, sorry, SI tomorrow is canceled, so don't go to that. Sorry, I didn't get an announcement about that. Yuri, what you've asked a couple of times which question is on the mini exam. Are you asking about this question? Because earlier in the session I had said that they're not on the mini exam. We just covered them today because they were in the slide deck. So as previously stated, the calculation of work using the material from 5.2 is not on this. So the systems and the surroundings. I got you. If we have a system, which in this case we're going to make a pot, so this is, we're going to boil water. So the system is the pot containing a lid, and the surroundings, so this is our system. The surroundings is everything outside of this box. And so the question becomes, does the heat go into the system or out from the system? And you can determine the sign based on that. So in this case, we have the system here, and then we ask the question, does the heat, is Q positive or negative, depending on where it goes? This academy is in Florida. It's a college course that happens to be run on YouTube. So I feel like Jane had questions, and I'm trying to find out where they went. Jane, am I answering any of your questions, or am I just drawing stuff on the board that is not helping? And it's totally acceptable to say, I'm still lost. I think, Jane, are you still in here? Because you might have just rolled out and I'm just hanging out. Jane, if you still have questions, why don't you send me an email and it'll be easier and we can chat via Zoom later this week. Y'all have a great rest of the day. I'm going to go ahead and close this session. If you have questions, send me an email or feel free to come to office hours at some point. Y'all have a great rest of the day.